Hi everyone and welcome to the internet. What we're going to be doing in today's chemistry lesson is having a look at the structure of metals. So hopefully by the end of today's lesson you can describe the structure and bonding in metals and explain the different features that then confers to the metals. To start us off though, we've got a couple of questions based around our previous lesson, so have a go answering those in your books. First question then, the polymer of bromoethene would be polybromoethene, 1 mark for that one. And for our second, hopefully you said thermosoftening for 1 mark, and then you needed to explain it, so they've got no crosslinks, 2nd mark, and that means they can change shape easily for our 3rd mark. So give yourself a total out of 4 for your starter. What we've got on the screen now then is one sentence with a couple of words missing that I'm hoping you can fill in just from your general knowledge, and then a question at the bottom for you to have a go at answering. So write down the sentence, filling in the blanks, hopefully with the right words, and then see if you can answer the question underneath. Let's make sure we got the right words in our sentence first of all. So all metals except mercury, so mercury is the only metal that is not solid at room temperature, are in the solid state at room temperature. Now, if we think about mercury, that's the one that's a liquid at room temperature. And if you've seen the old Terminator films, then where they've got the T2 that's going back into 1, then that was actually mercury on a board that they were rolling around and it all joined together. So mercury is the only metal that is a liquid at room temperature. All of the others are solid. So in terms of how the metal atoms are arranged, then what we actually find is that because metals are a solid at room temperature, then the atoms must be arranged in that closely packed regular arrangement. So you've got the picture at the bottom there with all of the atoms in nice clean rows and no gaps between them, because remember, one of those key features about a solid is it cannot be compressed. And if you've got gaps between your atoms, you will be able to compress it. So the solid, no gaps between them, and they're in that regular arrangement. We could actually go a little bit further here, and we can describe the atoms as being arranged in a giant metallic lattice. So giant because there's many of the atoms joined together, and a lattice because they're arranged in a regular way. So make sure you've got those two sentences written down, and if you want to do a sketch of the picture at the bottom, by all means do so. The next thing we need to move on to is to look at this idea of how the individual atoms within the metal are actually held together to give us this structure. So we're going to look at something called metallic bonding. Now, in the metals, what we actually find is that the electrons that make up the outer shell of the metal atom will be lost. So rather than having all of the electrons held within their normal electron shells, once they're in this metallic structure, those electrons are lost from the outer shell and become what's called delocalised electrons. Now these form a C, if you like. They're not fixed in any given position. They're free to move around the atoms as they were, and they can then flow in all three dimensions. Now, because we've lost electrons from the atoms, they are no longer atoms, they are ions. And because we've lost electrons, then that means they're going to be positive ions. So what we end up with are positive metal ions and this sea of delocalised electrons around them. And those electrons are really special because they're free to move through the structure of the metal. Now, that's really important when we come to think of some of the properties of our metals, and hopefully we know that one of the key properties of metals is that they conduct electricity. And if we draw on some of our physics knowledge, hopefully we know that when electrical current is flowing, then charged particles, or the electrons, are moving through the structure. So because we've got delocalised electrons that are free to move, then our metals will conduct electricity. So if you ever get a question asking why something can conduct electricity, then you can always go with the answer, it has delocalised electrons which are free to move. And if it asks why something will not conduct electricity, it doesn't have delocalised electrons which are free to move. Make sure you've got those 3 sentences written in your book. I'll leave them up for another couple of minutes just so you've got a chance to write them down. When it comes to the actual metallic bond, then this will form as the result of these strong electrostatic forces of attraction between the negative delocalised electrons and the positive metal ions. So this is quite a common 2 to 3 mark question of the exam papers of old. And they always sort of say on there that you may draw a diagram if you wish. And the diagram that you should be aiming to draw is the one on the screen. So what we can see is we've got our larger circles with a plus in them. Those are the positive metal ions. And then the smaller, slightly darker grey circles around them, those are the delocalised electrons. Now, if you just drew the diagram and included the labels, you can't just draw the little circles with pluses and then leave it and expect to get the marks. If you drew the positive metal ions and labelled those, and the delocalised electrons, labelling those, then that would normally be enough to get you 2 of the marks. The third mark is then for saying that the metallic bond is the strong electrostatic force of attraction between the delocalised electrons and the positive metal ions. So what you've got on your screen there is the full 3 marks. The only thing I would say is when you're drawing these diagrams, they were a bit picky in the past about how many of those you had to draw. So make sure you do a minimum of 6 of the positive metal ions. Any less than that and they tended not to give you the marks. So that's why I've given you this one, because we've got plenty on there. It doesn't take you long to draw an exam, but it gives you maximum marks. So I'll leave this up for a couple more minutes so you can get the diagram and that sentence written down. So what we've got here then are two different ways to model our metallic bonding. So two different ways we can draw the same diagram to all intents and purposes. What I want you to do is, looking at those two diagrams, I want you to say which model you think is best and why you think that. So what we find then is, if we look at those two diagrams, one problem that they've both got is that the ions are not touching. Now that obviously doesn't suggest we have a metallic structure that's a solid. So that's one problem they both have. We've also got an issue that the electrons are way too big for the size of the ions. They're not in proportion at all. If we look at the picture on the left first of all, then this one does give us an idea about the fact it's a three-dimensional structure. But the problem with it is when you try to draw it, then it's not so easy to do. If you've ever tried drawing three-dimensionally, it doesn't always go well. And what we actually have are all of those electrons are shown as this just cloud of negative charge shown by the green shading, not as the particles they actually are. Then if we look at the diagram on the right, what we've got is something that's very easy to draw because it's just circles and some other smaller circles, and it shows the electrons as particles, so a couple of good positives there, but we can't see the fact that they have a charge on them, and we also can't see any of the different layers that make up the rest of the structure. It just looks like a flat two-dimensional image. So in all honesty, whichever one you picked, you could have justified. We were just looking for the fact that obviously they've both got positives and negatives. So when we talk about models, it's always worth bearing in mind they're not perfect. They always have these limitations. So see if you can summarise a couple of those points if you didn't get them all. First one, neither diagram has the ions touching. Second one, electrons are too large for the ions in both diagrams. For the diagram on the left, positive, it gives the 3D structure. Negatives, it's difficult to draw. Negative, the electrons are shown as this cloud, not as particles. And then for the diagram on the right, positive, it's easy to draw. Positive shows the electrons as particles. Negative doesn't show the charges on the delocalised electrons. And a negative that the particles in the layers behind aren't shown. So it looks just flat and two-dimensional. Final thing for today then are your plenary questions. So those of you with target grades up to a grade 5, 2 columns on the left. Those of you with target grades over a grade 5, it's the 2 columns on the right. So I'll leave these up for about 4 minutes today, but as always, if you need longer, hit pause, take as long as you need.